Hello, this is Tim Smith, the Academic Support Coordinator of St. John's River State College, St. Augustine campus. This video, Polynomial Functions, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will be discussing the definition of a polynomial function, the elements of polynomial functions, basic polynomial functions, local extrema, end behavior, real zeros, and graphing polynomial functions. A polynomial function of degree n is a function of the form p of x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 and so on until a sub 1 times x plus a sub 0, where n is a non-negative integer and a sub n is not equal to 0. A sub 1, a sub 2, a sub 3, and so on up to a sub n are coefficients of the polynomial. A sub 0 is a constant term, a sub n is the leading coefficient, and a sub n times x to the n is the leading term. As an example, if f of x is equal to 7x to the fifth plus 5x to the fourth minus 8x to the third plus 2x squared minus 4x plus 2, this is a polynomial of degree 5 with coefficients 7, 5, negative 8, 2, negative 4, and 2. Leading coefficient is 7, leading term is 7x to the fifth, and the constant term is 2. Reviewing the basic polynomial functions, f of x is equal to x squared. With a set of ordered pairs, we can sketch the graph. We'll do the same with x to the fourth and compare. Both of these functions have even numbered exponents, resulting in a graph that approaches positive infinity with x values increasing both negative and positive. Note the common elements to each, 0, 0, 1, 1, and negative 1, 1. Let's do the same with x to the third. We start with a set of ordered pairs and sketch the graph, then compare it to x to the fifth. These are both functions with odd-numbered exponents. In both of these functions, the graph goes to infinity with increasing positive x's and to negative infinity with increasing negative x's. Note the common elements 0, 0, 1, 1, and negative 1, negative 1. Note that the graph of any polynomial function will be continuous and will be a smooth curve with no breaks, corners, or sharp points. Given any polynomial function, if the point a, p of a, is the highest point on the graph within a defined interval, then p of a is called a local maximum value of p. If the point b, p of b, is the lowest point on the graph within a defined interval, then p of b is called a local minimum value of p. The local maximum and minimum points on the graph of a function are called the local extrema. If a polynomial function has a degree n, then the graph of p has at most n minus 1 local extrema. Similarly to the basic polynomial functions, the leading term of the more complex functions will determine the end behavior of that function. If the exponent n of the leading term is an odd exponent, then the shape of the graph will be similar to the x cubed graph, in that if the leading coefficient is positive, the graph will go to infinity with more positive x's and negative infinity with negative x's. If the leading coefficient is negative, then the graph goes to negative infinity with increasing x's and positive infinity with decreasing x's. If n is an even exponent, then when the leading coefficient is positive, the graph goes to positive infinity with increasing and decreasing x's. When the leading coefficient is negative, the graph goes to negative infinity with increasing and decreasing x's. This is called the end behavior of a polynomial function. If p of x is a polynomial function, then any real number c is called a zero of p if p of c equals 0. If p of c equals 0, then the graph of p has an x-intercept at x equals c. For example, we'll use a second-degree trinomial f of x is equal to x squared minus 2x minus 3. We can factor the trinomial into x minus 3 and x plus 1. This means that f of 3 equals 0 and f of negative 1 equals 0. Therefore, the graph of f of x has x-intercepts at x equals 3 and x equals negative 1. Note that in this case, the two zeros are not only real numbers, but also rational numbers. When this is the case, we can call the zeros rational zeros. For example, let's evaluate and graph f of x is equal to x cubed plus 2x squared minus 5x minus 6. The first obvious point we can establish is a y-intercept. Set x equal to 0 and we get the point 0, negative 6. Next, we'll be looking for other rational zeros. This is a third-degree polynomial and will have a maximum of 3 x-intercepts and 2 local extrema. Therefore, it could be factored into 3 binomials, each with the first term of x. If this is the case, then we can look at the constant term 6. Since any rational zero will be a factor of 6 over the leading coefficient 1, the second term of any possible binomial factor must be a factor of 6. These factors are 1, 2, 3, and 6. Since the constant term is negative, then either one or all of them will be negative. We will first try negative 1. If x plus 1 is a binomial factor, then f of negative 1 should equal 0. F of negative 1 equals negative 1 cubed plus 2 times negative 1 squared minus 5 times negative 1 minus 6, which simplifies to negative 1 plus 2 plus 5 minus 6, which does equal 0. We can enter that as an ordered pair and confirm x plus 1 is a binomial factor of our function. Next, we can use this x plus 1 and derive a trinomial factor by understanding the first term will be x squared and the last term will be negative 6. The x coefficient will then have to be 1, so that a negative 5x will be the sum of adding negative 6x and positive 1x. The remaining trinomial can then be factored into x minus 2 and x plus 3. This gives us two additional rational zeros at 2 and negative 3, which describe x-intercepts at 2, 0 and negative 3, 0. Since the leading term of this polynomial has an odd exponent and a positive coefficient, we can expect the end behavior of this polynomial to be going to positive infinity with increasing x's and to negative infinity with increasing negative x's. We can also find additional test points by solving for x values that are not already described between our lowest and highest x-intercepts. F of 1 will be 1 plus 2 minus 5 minus 6, or negative 8. F of negative 2 will be negative 8 plus 8 plus 10 minus 6, or positive 4. We can now sketch the graph with some expectation of accuracy. In another example, let's evaluate and graph x to the fourth minus 5x squared plus 4. This is a fourth-degree polynomial with a positive leading coefficient, so the end behavior is towards positive infinity for increasing both positive and negative x's. There will also be a maximum of 4 x-intercepts and a maximum of 3 local extrema. As before, we can arrive at the first point by setting x equal to 0, which gives us the y-intercept 0, 4. If the polynomial has 4 rational zeros, then the constant terms of the 4 binomials could be combinations of 4, 2, and 1, with either all negative, 2 negatives, or no negatives. We'll start with assuming that one of the binomials is x plus 2. If true, then f of negative 2 equals 0. Replacing x with negative 2 gives us negative 2 to the fourth minus 5 times negative 2 squared plus 4. This equals 16 minus 20 plus 4, which is 0. We can now confirm negative 2 as a rational zero, x plus 2 as a factor of our function, and establish an ordered pair, negative 2, 0. Next, we complete polynomial division. We'll use x plus 2 as a dividend and our polynomial as the divisor, inserting x cubed in x terms with 0 coefficients. Since x cubed times x is x to the fourth, it will be our first term. X cubed times x plus 2 is x to the fourth plus 2x cubed. Subtract to get negative 2x cubed, then bring down negative 5x squared. Negative 2x squared times x will give us a negative 2x cubed, and times 2 is negative 4x squared. Subtract again to get negative x squared. Bring down the 0x. Our next term will be negative x, which we multiply times x plus 2 to get negative x squared minus 2x. Subtract again to get 2x, then bring down the 4. We use 2 as our last term. Multiplied times x plus 2 gives us no remainder. We now have x plus 2 times the quantity of x cubed minus 2x squared minus x plus 2. Let's next assume that x plus 1 is a factor. If it is, then f of negative 1 should equal 0. F of negative 1 equals negative 1 to the fourth minus 5 times negative 1 squared plus 4. This equals 1 minus 5 plus 4, or 0. This confirms negative 1 as a rational 0. We can enter the ordered pair and complete another polynomial division, this time using x plus 1. Again, place x plus 1 as the dividend and our remaining polynomial as the divisor. We start with x squared times x plus 1 equals x cubed plus x squared. Subtract to get negative 3x squared. The next term will be negative 3x times x plus 1 is negative 3x squared minus 3x. Subtract again to get 2x, then bring down the positive 2. Our last term will be 2 with no remainder. We are left with the quantity of x plus 2 times the quantity of x plus 1 times the quantity of x squared minus 3x plus 2. The remaining trinomial can then be factored easily into x minus 2 and x minus 1. These factors add to the list of rational zeros 2 and 1, and add the ordered pairs 2, 0 and 1, 0. Using the four x-intercepts and the y-intercept, and the known end behavior, we can now approximately sketch the graph. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.